Download this code from codegive.com, link in the description below. Demystifying bounds checking and off-by-one errors in C arrays. Arrays in C are a powerful but unforgiving tool. Their direct memory manipulation capabilities grant flexibility and performance, but this comes at the cost of responsibility. C does not inherently perform bounds checking. This means the compiler and runtime environment generally won't automatically prevent you from accessing memory outside the allocated bounds of an array. This lack of automatic protection makes understanding and manually implementing bounds checking and guarding against off-by-one errors crucial for writing robust and secure C code. This tutorial dives deep into these concepts, providing a comprehensive understanding, practical examples, and best practices to help you avoid common pitfalls. 1. What are arrays in C? An array in C is a contiguous block of memory that holds elements of the same data type. You declare an array by specifying its data type, name, and size. Data type determines the type of elements the array can store, example int, float, char. Name a unique identifier for the array. Size the number of elements the array can hold. This is fixed at compile time, for statically allocated arrays. Key characteristics of C arrays contiguous memory array elements are stored adjacent to each other in memory. This allows for efficient access using pointer arithmetic. 0 based indexing array indices start at 0 and go up to size 1. So, in numbers 5, valid indices are 0, 1, 2, 3, and 4. No built-in bounds checking the C compiler and runtime generally do not automatically check if you are accessing elements within the valid range of an array. 2. What is bounds checking, and why is it missing in C? Bounds checking refers to verifying that an array access, read or write, is within the valid range of indices, 0 to size 1. If you attempt to access an element outside this range, it's called an out-of-bounds access. In languages like Java or Python, the runtime environment typically performs bounds checking. If you try to access numbers 5 in a Java array declared as int numbers equals new int 5, a runtime exception, example array index out of bounds exception, will be thrown, stopping the program and preventing potentially catastrophic errors. Why C doesn't have automatic bounds checking performance checking array bounds on every access would add overhead to the execution of the program, potentially slowing it down. C prioritizes speed and allows programmers to optimize for performance. Direct memory access C is designed to give the programmer direct control over memory. Bounds checking would restrict this control and make it harder to perform certain low-level operations. Historical reasons C was designed in an era when memory was scarcer and performance was paramount. Automatic checks were considered a luxury. 3. The consequences of out-of-bounds accesses. When you access memory outside the bounds of an array in C, the behavior is undefined. This means anything can happen, including reading garbage data you might read data from a memory location that's not part of your array. The value you read could be anything and will likely be incorrect. Writing to arbitrary memory locations you might overwrite data in a memory location that's used by another variable, data structure, or even the operating system. This can lead to data corruption, crashes, or even security vulnerabilities. Program crash the operating system might detect the invalid memory access and terminate your program with a segmentation fault or a similar error. Silent data corruption your program might continue to run without any immediate errors, but the corrupted data can lead to unexpected and difficult to debug problems later on. Security vulnerabilities. Out-of-bounds writes can be exploited by attackers to inject malicious code into your program or to gain control of the system. Buffer overflows are a classic example of this type of vulnerability. 4. Manual bounds checking, your primary defense. Since C doesn't do it for you, you must implement bounds checking manually. This involves adding code to your program to verify that array indices are within the valid range before accessing elements. Here's a basic example. Explanation asterisk. 1 is valid index, int size, function asterisk. This function takes the index to be checked and the array size as input. It returns true if the index is within the valid bounds, 0 equals index size, and false otherwise. 2. Define array underscore size 5 asterisk using a define preprocessor directive or a const int variable, example const int array underscore size equals 5, to define the array size is good practice. It makes the code more readable and maintainable. If you need to change the array size later, you only need to modify it in one place. 3. Checking the index asterisk before accessing numbers index, the code calls isValidIndex to verify that the index is valid. 4. Error handling asterisk. If the index is invalid, an error message is printed to the console. This helps to prevent undefined behavior and makes it easier to debug your code. 5. Common scenarios requiring bounds checking. User input when an array index is provided by the user, it's crucial to validate it. Users might enter invalid or malicious values. The example above demonstrates this. Looping through arrays when iterating through an array using a for or while loop, ensure that the loop counter, index, never goes beyond the array bounds. This is a very common source of errors. Dynamic array allocation when using functions like malloc to allocate memory for an array dynamically, you need to keep track of the allocated size and perform bounds checking accordingly. Pointer arithmetic while powerful, pointer arithmetic can easily lead to out-of-bounds accesses if not used carefully. Always ensure that any pointer operations stay within the valid memory region. 6. Off-by-one errors, a subtle but dangerous pitfall. Off-by-one errors occur when you are one off in your indexing or loop control. They often result in accessing the element before the beginning of the array, index -1, or after the end of the array, index equals the array size. These are a specific type of out-of-bounds error. Common causes of off-by-one errors incorrect loop condition using instead of equals or vice versa in a for or while loop condition. Misunderstanding zero-based indexing forgetting that array indices start at 0, not 1. Calculating array sizes incorrectly especially when dealing with dynamically allocated arrays or arrays derived from other data structures. Example of an off-by-one error Why this is wrong The loop condition I equals array underscore size allows I to take on the value of array underscore size, which is 5. However, the valid indices for numbers are 0, 1, 2, 3, and 4. When I is 5, the code attempts to access numbers 5, which is outside the allocated memory. The correct way The loop condition I array underscore size ensures that I only takes on values from 0 to 4, preventing the out-of-bounds access. 7. Best practices for preventing bounds checking and off-by-one errors. Always use a header file or define for array sizes. Define the array size in a single place, example a define or const int, and use that constant throughout your code. This makes it easier to change the array size later and reduces the risk of inconsistencies. Asterisk use size of carefully. Asterisk the size of operator can be useful for determining the size of an array, especially when passing arrays to functions. However, be aware that size of will only return the size of the array in bytes, not the number of elements, if the array is passed as a pointer to a function. Asterisk initialize arrays. Asterisk always initialize arrays when you declare them. This can help to prevent unexpected behavior if you accidentally read an uninitialized element. Asterisk defensive programming. Asterisk adopt a defensive programming mindset. Assume that errors will happen and add checks to your code to catch them early. Asterisk code reviews. Asterisk have your code reviewed by someone else. A fresh pair of eyes can often spot errors that you might have missed. Asterisk static analysis tools. Asterisk use static analysis tools to automatically detect potential bounds checking and off-by-one errors in your code. These tools can help you find problems before you even run your program. Popular static analysis tools include *check*, a free and open source static analyzer for C/C++ code. *Covariety scan*, a commercial static analysis tool that can detect a wide range of defects, including buffer overflows and other security vulnerabilities. *ClangTidy*, a Clang-based C++ linter tool. *sanitizers, address sanitizer, undefined behavior sanitizer. Compile and run your code with sanitizers enabled. These tools insert runtime checks that will abort the program if they detect an out-of-bounds access or other undefined behavior. *address sanitizer, ASAN detects memory corruption errors, including heap and stack buffer overflows, use after free, and double free errors. *undefined behavior sanitizer, UBSAN detects a wide range of undefined behavior, including integer overflows, division by zero, and null pointer dereference. Example using address sanitizer, ASAN, and undefined behavior sanitizer, UBSAN, with GCC*. 1. Compile your code with the fsanitize equals address undefined flags*. *fsanitize equals address, enables address sanitizer. *fsanitize equals undefined, enables undefined behavior sanitizer. *G, adds debugging information to the executable, which can make it easier to debug errors detected by the sanitizers. *miprogram.c, compiles the miprogram.c file and creates an executable named miprogram. To run your program if the program performs an out-of-bounds access or exhibits undefined behavior, the sanitizers will print an error message to the console and terminate the program. The error message will typically include information about the location of the error in the code. 8. Example with dynamic memory allocation and bounds checking. Explanation*. 1. Dynamic memory allocation*. Dynamic array equals, int*, malloc, array size*, size of, int, allocates memory on the heap to store array size integers. The malloc function returns a pointer to the allocated memory. *if, dynamic array equals null, checks if the memory allocation was successful. If malloc fails to allocate memory, it returns null. 2. Initialization*. The code initializes the dynamic array to some known values, 0, 10, 20. This is good practice, especially when debugging. 3. Bounds checking*. The isValid index function and the if statement are used to check if the user provided index is within the valid bounds of the dynamic array before accessing the element. 4. Memory deallocation*. Free, dynamic array, releases the memory that was allocated by malloc. It is crucial to free dynamically allocated memory when you are finished with it to prevent memory leaks. Dynamic array equals null, sets the pointer to null after freeing the memory. This helps to prevent dangling pointers, pointers that point to memory that has already been freed. Attempting to dereference a dangling pointer will lead to undefined behavior. 9. Working with strings in C. Strings in C are simply arrays of characters, terminated by a null character, \0. Bounds checking is even more important when working with strings because buffer overflows are a common security vulnerability. Key points for string handling ***. Null termination **. Always remember that C strings must be null terminated. If you create a string without a null terminator, functions like strlen and printf, %s, will continue reading memory until they encounter a null character, potentially leading to out-of-bounds reads and crashes. *fgets for safe input *use fgets to read strings from the user instead of scanf, %s, or gets. Fgets allows you to specify a maximum number of characters to read, which helps to prevent buffer overflows. Remember to remove the trailing new line character that fgets might include. *strncpy for safe copying *use strncpy to copy strings instead of strcpy. strncpy allows you to specify the maximum number of characters to copy, preventing buffer overflows. However, strncpy may not null terminate the destination string if the source string is longer than the specified length. You might need to manually add a null terminator to ensure the destination string is properly terminated. *stringat for safe concatenation *use stringat to concatenate strings instead of stringat. Stringat allows you to specify the maximum number of characters to append, preventing buffer overflows. *strlen to determine length *use strlen to determine the length of a string. This is important for bounds checking and for allocating memory for strings. 10. Summary. Bounds checking and avoiding off-by-one errors are essential for writing safe and reliable C code. C gives you the responsibility to manage memory directly, so it's up to you to ensure you are accessing memory within the bounds of your arrays. By following the best practices outlined in this tutorial, you can significantly reduce the risk of these errors and build more robust and secure applications. Remember to utilize manual bounds checking, static analysis tools, and sanitizers during development and testing to identify and fix these types of errors early in the process. Good luck.